So we've been looking at limits so far in this class, and now we're going to look at the precise definition of a limit. So far we've been saying, oh, we could, we're getting closer and closer and closer to that X value. What is that Y value that we keep getting closer and closer to? So we wanted to define this a little more mathematically. And this is the formal definition of a limit. And so let me kind of see if I can make this a little bigger. So let's read through what that formal definition says, and then I will kind of draw a picture and try to explain it with a graph. So it says, let f of x be a function defined on an interval that contains x equals a, except possibly x equals a. Then we say that the limit as x approaches a of f of x equals L. If for every epsilon greater than 0, there is a delta greater than 0 such that the absolute value of f of x minus L is less than epsilon whenever 0 is less than the absolute value of x minus a and the absolute value is less than delta. Okay, so a couple things. Just symbol-wise, this kind of cursive looking E is a Greek letter epsilon. And I don't know how I would explain what that looks like, but this is the Greek letter for delta. Okay, so let's kind of nitpick this. So let f of x be a function defined on some interval. So let's look at a graph. Something like this. That contains x equals a. So let's just put x equals a here. So it's possible that there's this open circle here at x equals a, because it said it might not actually accept possibly x equals a. But let's just keep it as closed for now. And then we say that the limit as x approaches a, so just like we were doing before, as we're getting closer and closer to x equals a on the left and the right, so this would be where our f of x value is. Which if we plug in a in there, this would equal L. So this is actually f of a. So if for every epsilon greater than 0, so basically what we're trying to do is we're going to have some value of epsilon greater than 0, infinitesimally small, as small as we can get it. But I'm going to put this on, think of this as kind of blown up on my graphs just so we can see it. So we're going to choose some value of epsilon, and we're going to go up epsilon, that distance of epsilon from L, and we're going to go down the distance of epsilon from L. So if we can find some value of epsilon bigger than 0, such that there is some delta that is greater than 0. So basically, let's go back. So this is like the y value right here. Let's see what x would correspond to it. So I'm just going to come up to the graph and go down to see what x value corresponds to that L plus epsilon value. So we have an x value right here. And then if I did the bottom bound, so going over to the graph and coming down, this would be where our x value is. So if we have this value of epsilon that we want to be within this distance from L, either epsilon up or epsilon down, plus or minus the y value, we want to choose delta so that we can always be within that interval of L. So we can stay within the interval of L plus epsilon and L minus epsilon. Okay, so notice that actually in my picture, and this is possible that this happens, notice that this value in here, it looks like this distance in here between these two values. So this looks like this interval in here is actually bigger than this interval in here. And so if I was trying to figure out what delta was in this case, I would have to choose the smaller value. For the distance. Because for some reason, let's say that I'm looking at this and let's erase this. And I decided to choose my delta to be this bigger distance over here. Notice that if I add that distance, this distance in here onto this side, and I had chosen that to be my delta, notice that when I come up to the graph, I am not within the boundary that I wanted it to be. So we have to choose our delta so that we're always going to be within this boundary of L minus epsilon and L plus epsilon. So we want to stay within this, I guess we can call it a neighborhood. So we need to choose delta. To stay within our neighborhood. So maybe we're having some game or something, and you're giving me some value of epsilon in here, and you're saying, okay, can you choose a delta that would even get you inside this interval? So maybe you want to even shrink that value of epsilon infinitesimally small as we can get it. So maybe you chose your epsilon to be within these bounds. And if you did that, if the limit exists, you should be able to come back and find some delta so that you will always stay within that bound. So that's kind of the idea behind this. They're going to say, okay, given an epsilon greater than 0, could you figure out what that delta has to be in order to always stay within that bound? So recall that absolute value, this is just saying the distance. Remember, absolute value is just the distance. So again, this absolute value of f of x minus L is less than epsilon. So recall to drop absolute values of inequalities, and it's a less than sign, we sandwich this in between. So this is equivalent to saying, well, this is the same thing as negative epsilon is less than f of x minus L, which is less than epsilon. So if I isolate my function f of x in between those two inequalities, let's add L to all sides. So if we add L to all sides, this would be L minus epsilon is less than our function f of x is less than adding L epsilon plus L. So again, just pictorially, you have some L value in here and you're choosing some epsilon. So in this case, our Y value L plus epsilon would get us here. And if we subtract epsilon, that would get us down here, and that Y value we would say is L minus epsilon. Same sort of idea on the definition when you have this. So we have 0 is less than the absolute value of x minus a, which is less than delta. So this is just the distance again. So these aren't too bad when we have a linear function, and we're kind of working backwards when we're trying to prove that a limit exists. So let's look at the following. So we want to show that the limit as x approaches 4, we want to show that the limit as x approaches 4 of the function 2x plus 3 is equal to 11. So recall, we were just doing direct substitution, and we can see that we would get 11 there. So with direct substitution, it's easy to see. Right, so if we went in there and we plugged in a 4 wherever we saw an x, we would have 2 times 4 is 8, plus that 3, 8 plus 3 is 11. So we can see with a direct substitution that we should get that limit is 11. But we want to go through now and prove this mathematically using the delta epsilon proof. So first thing is kind of identifying what is what. So we're looking at the limit as x is approaching a of f of x equals L. So our L value here that we're approaching, that Y value of that line was 11. So I know that L is equal to 11 in this case. X is approaching A. So what value are we approaching? My A value in this case is 4. So A is equal to 4. And then my f of x function. So notice that f of x, that's what we're taking the limit of. We're taking the limit of 2x plus 3. So our f of x value in this case is this 2x plus 3. So first thing to figure out, what is the x value that you're getting closer and closer to? What is that function that you're looking at? And what is that y value we're trying to show that the limit is? Okay, so once you've determined that, we're going to first start with f of x minus L. So all you want to do is look at what f of x minus L is inside the epsilon. I'm sorry, inside the absolute value, which is less than epsilon. So let's write that out. So I'm going to rewrite this. The absolute value of f of x, which we just said was 2x plus 3, minus our L, and our L value in our case was 11. We want this to be less than epsilon. Okay, so we've set it up. We can start. Now what we're trying to do is take what we just set up, that absolute value, and we're trying to manipulate this to look like this x minus a. Once we've manipulated it to look like this x minus a, then we can see what delta is going to be. So first thing I'm going to do with my absolute value, let's just go in there and let's combine like terms. So I have the absolute value of 2x plus 3 minus 11. So this is really the absolute value of 2x. So 3 minus 11, I have minus 8. And that absolute value is less than. epsilon. So I can, again, drop these absolute values. Do I really need to? I don't think so. That doesn't look like what I'm trying to get at, though. What I'm trying to get at is x minus a, which is, in our case, x minus 4. A was what value we're approaching, which was 4. The x value we're approaching. So I notice I can almost manipulate this. Notice that if we factor out a 2 from inside that absolute value, so this could be rewritten as 2 all times the quantity x minus 4, and our absolute value is less than epsilon. Well, 2 is a positive number, so it doesn't matter if I leave that inside the absolute value because it's multiplication in between, or I can pull it out. So this is the same thing as 2 times x minus 4 is less than epsilon. So we're almost to what we're trying to manipulate it to look like. And if I just divide both sides by 2, then we have that. So here we would have then x, the absolute value of x minus 4, and the absolute value is less than epsilon divided by 2. So once you've manipulated it in that form of absolute value of x minus a, then we can tell what we're going to choose our delta to be. So this is what we want to choose delta to be. So we're going to choose delta to equal epsilon over 2. So choose delta, what you got on the right-hand side of the inequality. In our case, we just said that delta was epsilon divided by 2. Okay, so really what we just did with those first 4 steps was kind of working backwards on our proof. So now we're going to do the proof by now that we have what delta is. Okay, so now we're going to work backwards, the proof. We're going to look at, so we're going to let delta equal epsilon divided by 2. And since that's the case, we're going to rewrite this x minus absolute value of x minus a. In our case, that is the absolute value of x, a is 4. So x minus 4 is less than delta. The delta we chose to be epsilon over 2. And now we're just going to kind of move forward what we had just done and solve for delta here. So now our goal is to get back to what we originally started with. And so let's do that. So I can multiply both sides of my inequality by 2. 2 is a positive number. That's not going to change anything with a sign. So multiplying this by 2, multiplying this side by 2, that would clear our fraction, leaving us with the absolute, or 2 times the absolute value of x minus 4 is less than epsilon. Because that number is positive, that coefficient outside of the absolute value is positive, it's the same thing as if it was inside. So we can say, well, this is the same thing then as 2 times the quantity x minus 4 inside that absolute value, which is less than epsilon. We can now distribute. So we have 2x minus 8 is less than epsilon. But our goal is to make it look like this absolute value of f of x minus L. So right up here, this f of x minus L. So again, we're just going to do some manipulation. And so doing that, I can say 2x. Let's just rewrite negative 8 as a sum of 2 numbers. And so we want it to be plus 3, and then minus this 11 is less than epsilon. And so notice here, This is our f of x minus, and this is our L. Okay, so as long as we choose delta to be half the distance of what we want to move up from our y value and our down from our y value, then we'll always fall within that interval. So it's kind of a little funky. I'll let you take a moment and digest it and then ask any questions if you have any. We'll look at a couple more examples where these are linear. What we've been looking at, or this example, this was a linear function that we were looking at the limit. So this is not definitely the way that we really want to prove limits like this. We'd rather just go in and do our direct substitution. But this is mathematics. We kind of want things to be precise. And so what does it really mean to be arbitrarily close? And so this is a precise definition, formal definition of what a limit is. Okay, so there was a great question in the chat that's asked, can we choose any numbers that equals that -8, that -8 in there for that last step? If we chose any two numbers that sum to -8, our problem would be is that we couldn't manipulate it to look like this f of x function, what we were taking the limit of, and where that y value was going. And so we want to manipulate it or choose those two numbers so that we could get it in this form of the absolute value of f of x minus L. And the cool thing is really when we're doing this scratch work, we can kind of see how we manipulated it, right here before we had added our like terms. So you can kind of see what those two numbers are going to be. Any other questions?